Hello, this video is on section 510 on the natural logarithm and other functions defined by integrals. So something that's covered in this section that I won't talk about for very long is a way of reintroducing the natural log. So let's look at this integral. So you'll notice t here is what's called a dummy variable. T is the variable that just expresses that we are doing an integral. But x is the thing that this depends on. Or you can think that what this really means is if we graph this function f of t equals 1 over t, what we're measuring here is an area between 1 and x. As x moves, the answer moves. Now, by the fundamental theorem of calculus, the antiderivative there would be the natural log of the absolute value of t from 1 to x. So that would be the natural log of x minus the natural log of 1, assuming x is positive. Natural log of 1 is 0, so we get the natural log of x. So the natural log of x actually measures that area. And one could, in theory, say that's the definition of natural log. That's usually not how we think about it. We think of it as starting with this exponential function with base e and then taking its inverse to undo it with the logarithm. But there is a point of view, pardon me, that starts with the idea that this integral, it's a function using an integral, and it measures something, and what it measures is called natural log. So it's interesting from a historical point of view. But we'll see this in other ways. We can use integrals to define functions. And we've seen this already with the second part of the fundamental theorem of calculus. Let's look at this example. Here we're saying g is this function that basically tells us how much we get when we integrate f. So again, let's think of this in terms of a picture, and we'll interpret it in terms of area. I'm assuming things are positive so that the area makes sense. So this is actually the t-axis, if we're being careful. So here is our graph of f of t. And what this function is measuring, g of x is basically saying starting at a, which is a specific constant, and ending at x, how much area do we get? How much has been accumulated? Integrals can be thought of as an accumulation. If we start at a and end at x, how much have we accumulated? As x moves, this function changes value. And the second part of the fundamental theorem of calculus says that the derivative of that accumulation function is simply f. So if we define a function in terms of a definite integral in this very specific way, then the derivative of that function is just f of x. That's a basic fact you need to know. Right? It's sort of saying that derivatives and integrals cancel, which feels right, but this is in the context of a definite integral, not an antiderivative. Now, we can throw some wrinkles at this. So here, suppose that I have this function. K of x is the definite integral from a to h of x of f of t dt. Using this notation from before, k is g. G is basically my name for this function that measures the accumulated integral of f. But we're not measuring how much we get through x. We're measuring how much we get up to h of x. Start the integral at a and finish at h of x. That's what this is. So k of x is g of h of x. G is basically this function that does an integral, does a definite integral. And h is some other function. If we wanted to take the derivative of k, by the chain rule, the derivative of k would be outer derivative times inner derivative. My outer function is called g, so my outer derivative is called g prime of the thing inside, times my inner derivative with it, which is h prime. But g prime is f. So this is f of h of x times h prime of x. So if you are given some function defined in terms of a definite integral, but it doesn't end at x, taking the derivative involves the chain rule. This is one of the most complicated things that shows up routinely on the AP exam. Certainly there are standalone, weird, difficult problems. This is one that I've seen recur. So let's look at this one. The idea here is what M is doing, and I'm even going to avoid names here, but the idea, so I'll do this, I'll show you this one and then I'll give you an opportunity to try the next one. M is applying this integral function. I'm just going to call it int, but it's not ending it at x, it's ending it at x cubed. Right? Int is my abbreviation for this whole process that's measuring something in terms of a definite integral. So by the chain rule, this would be the derivative of that integral process, still with x cubed inside, times the derivative of the inside. But the idea is that the derivative of that integral process is just the function we're integrating. So what the derivative of that integral is this function 3 cosine of t, where here t is x cubed. So that's our derivative. The idea is sort of we're taking this thing, this non-x bound, and we're plugging that in to basically account for the fact that, oh, the derivative of that integral is basically the function. But then there's an additional chain rule step. So take a moment and try this one, hit pause, and using the same principles, figure out what would be the derivative of this function. Okay, and let's just note p is a function of x, s is the name of our dummy variable. So my outer function is an integral involving natural log of s squared. So my outer derivative would simply be that function, natural log of s squared, where s is root x. But then by the chain rule, I would have to multiply by the derivative of this thing. So this works out to the natural log of x times 1/2 x to the negative root 2, and we could write that in various ways, maybe like that. So you'll have a little bit of homework to practice doing this kind of thing. It is tricky, but after you've done a few examples, hopefully you latch on to the pattern. It's a combination of the second part of the fundamental theorem of calculus, which expresses this really simple idea that when a function is measuring accumulation using an integral, in this easy way where it ends at x, the derivative of that accumulation function is just the function we're integrating. But then it combines that with chain rule. All right, that's it.